everybody. Thanks for coming. If you don't know, today is Brazilian Day at ElixirConf. We have about 5 Brazilians speaking today. I'm the last one, and Guilherme across is also Brazilian. And of course, yesterday we had Jose. So that's, I think, 6 Brazilians. It might be the second most biggest nationality speaking here after Americans. So watch out. As I said, I'm Brazilian, but I live in London. And you might ask, why would a Brazilian move to London given the weather difference? And just so you know, I grew up in a place where the temperature during the whole year is around 70 to 75 degrees. So I live in London now, which is a bit different. But the reason I live in London is because I moved there to work for this company. You switch, and we do a bunch of cool things there. We do, of course, Elixir, Clojure, Ruby, Haskell, Golang, JavaScript. We use Docker to build containers, and we deploy everything in Cube. So that's quite a few things. And there are more things, smaller, but we do a lot of those things. This is our homepage. Actually, I don't know how the energy industry is here in America. I don't know how it is in Brazil. In Brazil, energy industry is pretty simple. You have only one supplier provided by the government, and you have to use the energy provided by them. In the UK, it's different. It's a private sector, which means there is about 60 to 70 different energy suppliers. So your switch is basically a price comparison website. And we started with energy price comparison. And as you can see in the menu there, we have broadband and TV, now mobiles, personal insurance, personal finance insurance. So it's a pretty interesting sector to work on. This is the product we deliver to people. It's basically a results table comparing different things, services, products. And we work in an environment that is pretty interesting with cross-functional teams. So we work pretty closely with data analysts and UX designers and engineers. We are all very, very close. Engineers are part of the product life cycle and decisions. So it's pretty fun to work there. If you want to come live in London, come talk to me. If you don't, if you just want to ask stuff about it, we have a pretty interesting idea around testing. We prefer monitoring over testing, so it might be very, very controversial, but I'm not going to talk about that today. Before I start the talk, I want to give a disclaimer. When I submitted the proposal, this application I'm going to talk to you about was in its very, very first few days, and we had a beautiful plan for it, which was to make it a stateful app. I will walk you through why that didn't happen. So who here has built an application that is totally stateful using Erlang or Elixir? Cool. I'm interested to talk about that. So there is this big thing there in our company called Rails, and we have this very old application in my team, which is the energy team, which is the oldest team there. And as trend dictates, we migrate away from Rails by building microservices. So now our application, our main application, it looks like that. I mean, it doesn't look like that. It runs in those two things. So half of our funnel is running Rails, and half of it is running Node.js, because we are migrating away from Rails and writing a very thin application, just doing the front-endy stuff using React, Redux, server-side rendering, all whatever buzzword you want to use to describe that kind of thing. So this Rails app is pretty big. And one of the things we do a lot at USwitch is A/B test. So that Rails application has a few classes and or modules that handle that kind of logic. Middlewares for people landing, and we're doing experiment assignment for these people. So we have a happy user, and they come to our website and they're like, hey, give me a page. And then our Rails app is like, okay, here's a page with an experiment. So essentially, we just grab that user ID and we'll deterministically assign them to an experiment. And we'll run that experiment, whatever that is. Might be a change in the view or some business logic, whatever that might be. But when we started running our application in two different stacks at the same time, half of it in Node, half of it in Rails, we had a problem. Our happy user came and he requested the page that was served by our Node app. And we were like, yeah, sure, but unfortunately, we can't give you an experiment because that whole logic is in our Rails app. The interesting thing is, oh yeah, of course, you could just expose that whole logic through an API, or you could redirect the user to the Rails app and have that assignment logic happen in Rails. But we're migrating away from Rails, and we want to deconstruct all these dependencies. So the decision was, well, we want to move away, and we're extracting those small services from this big Rails app. So the scenario then becomes, we have our Node app, or Rails app for that matter, and an experiment API. So this was a great opportunity to introduce Elixir. So user comes in, give me a page, Node app is like, wait a second, let me grab your user ID, and I want you to participate in this given experiment ID test. The experiment API returns whatever bucket the user is assigned to, and then Node app happily serves a page with an experiment. So what is this experiment API doing? It's an HTTP API, it's pretty simple. It has a list of experiments that it needs to do a lookup on to decide whether or not the user should be bucketed to the experiment, and a few other things. And the main thing it does, it will use that user ID, the experiment ID and the experiment version, to assign the user deterministically to an experiment. Why? Because every time the user comes back, he should have a consistent experience in the website. So we want to always make sure that we're bucketing them in the same way. At that point, our team didn't have any Elixir apps, and I was like, this is the perfect case, because it's so small. And we were like, oh, let's try it. If it sucks, we can rewrite it pretty quickly. So I brought Elixir in. So what does it do really? Essentially, it's this function. That's actually the real thing. I copied it from our code base, and it's pretty simple. It creates an assignment by receiving a new user ID and an experiment. Then it does a pick bucket that does a little bit of magic, and then returns an assignment with the user ID, the experiment ID, the version for the experiment, and the bucket ID. So this is the pick bucket magic. This is where we do the deterministic assignment. It's pretty simple. It creates a SHA with the user ID, the experiment ID, and the experiment version, and then does some encoding and parsing. Then that's going to give us a number, and then this weighted random basically is going to use that number to pick a bucket that has a certain weight. So sometimes we do weighted assignment. So let's say bucket A is supposed to have 80% of traffic going to that bucket and 20% of traffic going to bucket B. So this is all the weighted random does. It just takes that number and translates into that. So I know what you're thinking. That's pretty simple. The only data really you're handling there is experiments. So let's bring Redis in, or let's bring Postgres in, and of course not being using Elixir and knowing all the amazing things Elixir provides us with, we think, no, let's use GenServer or Agent or ATS. So that's what I thought. So storing an experiment, it's pretty straightforward. This is what an experiment looks like. It has an ID, a version, a flag, whether or not it's enabled, and buckets. You can have as many as you want. The reason it's a struct itself is because we can also provide the weight to it, as I said before. So simple data structure. How does it work then? Well, as we saw before, the Node app is going to go and query the experiment API and be like, okay, this is the user ID I have. Give me a bucket, please. So the experiment API essentially does this. It will have a high number of requests because every user that comes to our page or to our website will very likely be taking part in an experiment. So the read rate is pretty high. The response has to be consistent, so we provide a consistent experience to the user. And due to the high number of requests, there is a lot of lookup on the experiment data. So we can have multiple experiments stored at the same time in that API. And of course, because we're extracting that logic from Rails, which was doing that in its own application, we want this to be as fast as possible so we don't have any impact on the end user. So this is basically the whole flow of how things happen. Oh, sorry. Sorry, this is the update. So as I said, the get assignment, it does a lot of reads of experiments. But there are some cases where we do need to update experiments. And that smiley face, that's me or someone in my team. Usually we're going to go there to bump an experiment version because we changed something on what the experiment is, or we want to change the bucket weighting, or we even want to disable or enable the experiment. So the amount of calls we do to update an experiment is very, very, very small when compared to actually using it or reading it. So updating an experiment has a very low number of requests. Eventual consistency is not a problem for this particular use case. And because this operation is not a client-facing one, it can take as long as it needs to actually happen. So just to make sure. So these are the two requirements we have: getting an assignment and updating an experiment. On the left side, we have a very high number of requests that needs to be consistent, but fortunately there is no data being written anywhere. So we can use in-memory state to keep all that data. On the right side, we do have data being modified or written, or a state mutation, but that's a very, very low number of requests. And again, eventual consistency in this case is not a problem. So, okay, now that we understand the requirements, we have a few different options to actually store all that data. That is actually not big at all. So the first option is a GenServer/agent. In this case, agent is probably a better idea just because it's a very, very simple data structure. There isn't anything too complicated about it, so you just read and update it. ETS, Erlang term storage, which is built into the Erlang virtual machine, and it's pretty good. By the way, there is an interesting fact about on using these two. Apparently, doing lookups in a map is faster than using ETS to do lookups. So if you ever come across the situation where you can use either or. If it is a map, use the pure Elixir one. And of course there is Minija. So let's go through a few other things that we need to consider before we can even choose one of these three. So first of all, how do we persist this state across deployments? As we know, Erlang was conceived a very long time ago when containers really didn't exist, and you would be even doing hot code reloading or deployments, and you didn't really lose your state, or your in-memory state was always there available for you. But today it's not like that. As I said earlier, we deploy to Kubernetes, which means every new deployment is a new machine, a new memory space. So that's the first thing we have to consider. How do we persist state across different deployments? What will happen if my application crashes? How do I back up my data? How do I make sure I'm not going to lose anything if there is, for some reason, something happens and my application just crashes? Third, how do I make sure, or how do I propagate experiment changes across different instances? So if I have multiple instances of my application running, how do I make sure that an update to an experiment is going to be propagated across all different instances? And fourth, what happens when there is a network partition? So these questions are pretty standard if you're building a distributed system. So let's see how we would handle all those cases if we were using GenServer or agent. So as I said, we build containers with Docker and we deploy using Kubernetes. Who here is using these two technologies? So I'll do a quick run through how Cube works. So Cube is like this huge operating system handling multiple nodes, and there is a bunch of things. So if I were to explain it, I can't explain it because I don't really know about it. Our DevOps team takes care of it. I just use it, which is great. So Cube, but a general idea is you have two hosts, and these can be pure EC2 instances on Amazon, let's say. So host 1 and host 2, and you can see each one of them has two pods. A pod is a thing that it's a host in itself, and it's going to be running multiple containers. In our case, like Docker containers. So this pod, the idea behind it is that you group together containers that should be logically placed in the same place. So in this case, my application here is this pod 1 and pod on host 2, the yellow one. There is no guarantee when I do a new deployment where that new deployment is going to run. It could go run in host 1 or in host 2. I don't know. So I issue a deployment, and that same application is now initializing in host 1. So what that means is I can't really rely on the host, either host 2 or host 1, to keep my data, because again, that pod is initializing in a different host, so there is no access to disk, for instance. So pod 3 initializes, pod 1 is still running, then Cube, once pod 3 starts running, it will put pod 1 on host 2 through this whole termination process. And eventually, pod 1 will be terminated. So with that in mind, how can we persist state across deployments? Again, back when we used to just deploy everything in bare metal, this was a no-brainer. You had access to disk and you had shared memory. But now that's no longer the case, unfortunately. And so we have to do some workarounds. And there is some nice solutions. So the one solution I came up with, and I'm open to discussing it, is init containers and using Erlang term to binary and Erlang binary to term. So this is, of course, the case for GenServer and agent. So what is an init container? There is this thing you could read, but you're not going to read, and I'm not going to read it to you. But basically, an init container, the idea behind it is that you use, semantically, you use it to set up your pod. So in Cube, you have these pods running all your containers. An init container is something that runs before Cube starts your containers. So semantically, it means you do any kind of setup on your pod using that. Together with that, we can also use Erlang term to binary and binary to term. So this is a very, very efficient way that Erlang transforms terms into binaries, and you can just dump that to whatever you want. And also the deserialization of that is really, really fast. And as I said, this experiment, it's a very, very simple data structure. There won't be a lot of data. Maybe if there is 1 kilobyte, it's going to be too big. So using these two things, we can then do the following. Happy user comes in. In that case, it's me, because we're updating the experiment. So it's not really a client-facing operation. So I come in, do an update on the experiment. The experiment API simply will dump the experiment into AWS S3. So what that means is just going to use Erlang term to binary, and it's going to dump that into a file and then upload that to S3. Like that, I can guarantee that all my updates will be backed up and will be consistent. And finally, I just give a response saying, all good, your data has been persisted. So this, together with an init container, when we're in this state, essentially what's happening on pod 3, on host 1, is that we're going to be reading all that data that was dumped on the previous update from S3. So now, when my application on pod 3 starts running, it's going to pick up the state that was last backed up. Of course, there is one caveat here, which is, what if an update happens while that pod is initializing? So this is going to be answered when we start talking about how we distribute this application. And if I forget, ask me. So we actually resolved two of the things we had to consider. So how to persist state across deployments, and what happens if the application crashes. How do I back up my stuff? So it's a pretty simple solution, and you can probably write code to do that in maybe 20 lines of Elixir, even less. So the next two things are, how do I propagate experiment changes across different instances, and what happens when there is a network partition? So let's talk about distribution. I chose primary and replicas because it's simple enough, and because of the backup generation. If I have a primary node, it's going to be way simpler to always see that, oh yeah, there was an update executed. I'm the primary node. I'm just going to dump all my stuff to disk and then upload to S3 from this node. So that makes things simpler. So again, just to remind you, this updating of experiments is a very, very low number of requests. Eventual consistency is not a problem, even though with what I have here, this architecture will give me a strong consistency, as long as there is no partition. And again, this operation can be slow. So again, I'm happy. There is instance 1 of my application running, instance 2. I do an update to instance 1, receive an OK, then my friend comes over, does an update to instance 2, receives an OK, but now these two nodes are out of sync. So how do we fix that? Essentially, primary node, replica, there's an update. Primary will just replicate that. When it receives an OK from all its replicas, it will send an OK back. to me. And the same thing works if the request comes to the replica, there's an update, it calls the primary node, say, hey, I have an update. Primary is like, okay, all good, all has been replicated. Replica is like, cool, okay. So with that, in that scenario where I said, when we're doing deployment and while the new deployment is being initialized, if there's an update, when that new deployment comes in, that's going to essentially join as a replica for the current primary, and it's going to have its state synced. So it has a backup, it has a state to start with in case stuff went bad before, but also when it joins the mesh, it's going to be synced up to what's the current state in the cluster. So that resolves thing to consider 3. And what should we do in a case of a network partition? So again, primary, replica, update. When the replication fails, I chose here explicitly to fail in the primary as well. So I have a strong consistency. So I don't allow writes. And if I'm running a cluster mode, I don't allow any writes unless I can replicate. And same thing happens with a replica. If stuff fails, I don't really allow any writes. So because I have this simple property, which is there is a very, very, very low number of writes, there is a very high number of reads, and because I can really fail when a write can't be successful, this allows me to run all these things, to keep all these things in memory. So still, there are 2 caveats. First one is concurrent reads. As we know, this is Erlang, and it uses actors. So that means every read is going to be a message in that mailbox. So if there are too many requests coming in, I have too many instances, I have one instance that is taking too many requests, it could be that that mailbox will be full and eventually things could get slow. Because this is so simple, it's very unlikely for this to happen, but it could, because there are no concurrent reads. And of course, the biggest caveat here is maintaining all the code around the distribution bit. Of course, there's some open source things, but I didn't find anything that was particularly welcoming. So it's still a problem. So having said that, how does ETS amnesia fit into this? So let's go through ETS really quickly. So ETS, as probably everybody here knows, is Erlang term storage, and it's pretty good. The deployment goes exactly the same, nothing changes there. The only difference would be persisting state across deployments. So ETS uses memory. There is DTS, which uses disk, but doesn't really help us because, again, when a new pod comes in, there's no guarantee that it's going to be run on the same host. Therefore, there's no guarantee that you're going to have that same disk. So same principle, you use init containers and ETS tab to file and ETS file to tab, which works about the same way as I explained previously for term to binary and binary to term. So essentially, we do the same thing. When a request comes in, we dump experiments. Then again, we grab that ETS table, we dump it and upload it to a S3. Like that, we can keep these 2 points is still satisfied. Again, we still have the other 2 points. So distribution, actually ETS doesn't have any distribution. So again, we're going to have to replicate the same kind of solution we had for GenServer and agent. And the same properties are kept. But ETS does allow concurrency. So if we take a look at the documentation for ETS, on the right-hand side, you can see on the tweaks section, it has write concurrency and read concurrency. So you can set these things so basically you can do concurrent reads. But on the left-hand side, I recommend you read that before you tweak those things, because your system needs to have certain properties for you to be able to use this concurrency thingies in ETS. And most importantly, the third paragraph says that if you turn these two things on a situation where your reads and writes are interleaved, meaning they're about the same in quantity, this is actually going to degrade your performance. But because our system has a very high number of reads and very, very low number of writes, this actually would help very much, and we would get concurrency, which is a plus if we need it. So cool, concurrent reads, we got them. But what about writing and maintaining code? That's not very good, not in my experience. Code should be deleted always. So we have Mnesia. So Mnesia, unfortunately, it does have it is built on top of ETS, which then it's built on top of DETS, which is disk ETS, but it still cannot use a cloud as its backend. It still relies on disk, but again, you can use the same technique with init containers and a backup sort of thing to dump the data and upload it to S3. It will have concurrency because it's built on top of ETS, and it does provide distribution. So it does it has primary plus replicas without consistency guarantees, which is not a problem in our system. We tolerate eventual consistency. So cool, replicas give no consistent guarantees. This is a problem if you cannot tolerate that sort of thing. So overall, it's all good. We could have built this application with these three things, but anyone here thinks it's easier to build an application like this or to use a database? If you think using a database is better, raise your hand. And I assume everyone else would have done that, and I applaud you. You're very brave. There are some libraries out there to help you build this kind of application. One of them is Spearage. It helps you to basically do clustering inside Kubernetes using DNS. It's very nice, so that would help a lot. This agent is something I just found today. It's used, basically, it provides you with Raft consensus protocol to distribute your Elixir agents, which is pretty cool as well. And this guy, is Kirino, I guess. He has a few cool projects in GitHub regarding distribution. And last but not least, there is this Phoenix framework Firenest, and I've seen a few Elixir core members working on this project, and it is in its very early stages. I'm not even sure I should be mentioning it here, but I suppose the plan with it is to provide a lot of distribution primitives and things like that to make projects like this possible. So in conclusion, first thing first, define all the application characteristics before building anything. So understand exactly what kind of property your application needs to have before you jump and start writing a GenServer to keep your state in memory. An external database is your best option, in my experience in this case, unless you really, really need to get rid of network latency. And again, this is something that is true for an application that has these properties I described here. And this is mainly the issue. When we go down and analyze an application and what properties it needs to have, we're going to be having a lot of different options and things that need to be met. And a database, the good thing with it is that it has so many guarantees for you, and you don't need to write any code. You just plug in and you go be happy. I hope one day we have enough libraries that will make our life easier, like we have with GenStage and some other things that are so easy, and we can build complete solutions. So I'm really looking forward to seeing solutions, things that help us build this kind of application in an easier way. So yeah, as I said, this future hopefully will come. And yeah, that's pretty much it. Thank you very much.